All right, everybody, welcome in. Special edition of Composite Materials. Sorry about Friday. I had some issues with my car and the appointment went long. I could not get out of there. So, recording this exam review now. My weekend got away from me a bit, but we'll get into it now. It's Sunday the 15th, 6:30 in the evening. Packer game's about to come on. Hope I can get this done before then. Yeah, this is just going to be an exam review. I'm going to cover two things, the sort of qualitative type handout that I sent to you guys, and also sort of the test, the fake test, mock exam that I sent out. And we'll try to do this like relatively quickly. A beauty about YouTube too is you can speed me up. I'd say go probably 1.5 speed or so. Get through this nice and quickly. All right. So let's get right to it. I'm going to share my screen and we'll just get right to it. So I'm sharing here on my screen. This is kind of like my writing pad, where I'm just going to sort of make notes on the document that I already presented to you. So this document you can find on Canvas in the modules tab. This is the final exam review. So this is the last sort of qualitative type review that I have for you guys. So we'll kind of just go through these things one by one. And this is strictly for the last couple of weeks of the class. Now, the final itself is cumulative. So what I have written here is only from like exam two until now. So you will be responsible for everything for the class, but the final is going to emphasize more of the more recent stuff. Okay? So away we go. Classical lamination theory. Off we go. Hand calculations. Be ready to transform stresses and strains between principal and arbitrary coordinates using transformation matrices. Okay, so that is just essentially saying, all right, I need stress 1, 2. That's the transformation matrix T times stress that I might have in an XY coordinate system. Similarly for strain, if I want strain in the 1, 2 coordinate system, I need a different matrix, that's the T star matrix, times strain that I might know in XY. So this comes up a lot when we're talking about laminate theory, because lamination theory, you have a global XY coordinate system, and a lot of times you need to transform into the 1, 2 coordinate system so that you can do things like failure criteria, so to say. So I want to know the stress of any one particular layer, and this is the way that we do that with the T and the T star matrices. Remember T and T star, they'll use the angle theta and cosines and sines of theta to get you to that. Okay, so next, you'll want to calculate entries of ABD matrix. All right. So ABD matrices, you're going to have to do some of these by hand on the final. Like that's not a secret. I'm not going to make you calculate every entry, right? So each of these is a 3 by 3 matrix. I would probably only ask you to calculate one entry of each of the three types. So just remember kind of how we do those calculations. Calculating A, this is the summation from K equals 1 to N of Q bar K times ZK minus ZK minus 1. Okay, where we've done a lot of these types of problems now. ZK and ZK minus 1, these are coordinates of the laminate. And remember, we always assign our coordinate system for our laminate at the midplane. So here, this is probably your X direction, this is your Z direction. And so if you have a laminated material with, some various layers, then this would be like Z0. Here, this would be like the coordinate Z1 and Z2 and Z3 and Z4. Okay, so that's calculating the A matrix. And then the Q, this is the off-axis stiffness matrix. So this is stiffness matrix of layer K. Okay, so that's the calculation of the A matrix. The calculation of the B matrix, don't forget your 1/2. This is another common thing that happens on the final. People forget their 1/2 term and their 1/3 term. So here now we got summation K equals 1 to N of Q bar K. Here now we have ZK squared minus ZK minus 1 squared. All right, and don't make the mistake of taking this entire term squared. That's wrong, okay? Don't do that. You want each of these individual entries squared, right? So that's another common mistake I tend to see on the hand calculation portion of the final. All right, the D matrix looks very similar, except now you have 1/3. Summation K equals 1 to N of Q bar K times ZK cubed minus ZK minus 1 cubed. All right, so those are your A, B, and D matrix calculations. And we've done a lot of this computationally, so make sure that you brush up on how to actually do these by hand, because I think I've only ever forced you to do it once by hand for like one entry or so. So make sure you know how to do that. It's definitely going to come up on the final. So um, got to practice that one. All right, so that's that. Calculate loads and moments per unit length given ABD matrices and limited mid-plane strains and curvatures. Okay, so here now we're talking about the inversion. So we'll get rid of a lot of this stuff here. Make space for ourselves. Let's put something new in here. All right. So here now, calculate loads and moments per unit length. So here this is loads and moments per unit length, N and M. Given ABD matrices and lambda midplane strains and curvatures. So if you have ABD and you have midplane strains and curvatures, this is your calculation. And remember, this is a 6x1, this is a 6x6, and this is a 6x1. Okay? So that's the most simplistic way that you can represent the formula. All right? So there you go. All right, on to theory questions. For theory questions, understand the physical interpretation of ABD. Yeah, this is really important just from walking away from this class and understanding it perspective. So if you just kind of take a look at this equation up here that dictates loads, the relationships to strains and curvatures, then what I'm basically asking is, well, what is the A matrix physically representing? And so if you break this out, you say that like, okay, N is equal to A times epsilon naught plus B times kappa. All right. So what is the A matrix here? Well, the A matrix here is relating in-plane loads to in-plane strains. So when you think about the A matrix, it's relating in-plane loads. So tension in X, tension in Y, and in-plane shear to strains which develop in the middle of the laminate. So how much longer or shorter in X, how much longer or shorter in Y, and how much shear do you get, either positive or negative, at the midplane of your laminate, and kind of like the XY coordinate system. So that's what the A matrix relates. It relates in-plane loads to in-plane strains. The B matrix has sort of two definitions, and so it shows up in both the calculation of moment and load. So we got to kind of take a look at that here quickly. Here's your calculation for the moments. Okay, so the B matrix, you kind of see two different things. So here, the B matrix is going to relate in-plane loads to curvatures. This is the weird one that happens with composites, right? Isotropic materials don't have this B matrix, right? The B matrix for isotropic materials is zero. And so the B matrix, it kind of has two different places it shows its head. One is relating in-plane loads, N, to curvatures, which might exist in the laminate. So that's a strange thing. Imagine pulling on a laminate and then it curving somehow. Yeah, that just happens with composites who have, non-symmetric stacking sequences. All right. So that's one thing that the B matrix does. It relates in-plane loads to curvatures, but it also relates applied moments to in-plane strains, which is also, again, very weird. I'm going to bend this thing and it gets longer or shorter, like at the midplane. Very unusual behavior. And it just happens because you just have these stacking sequences that just give fibers in a lot of different directions. Okay? So that's the B matrix. Finally, the D matrix will be a little bit easier to understand. The D matrix relates moments to curvatures. It's something that you would expect even from isotropic materials, right? Where I apply some bending moment and then I get some curvature out of my material. Okay, it's very common to see that in isotropic materials, so hopefully that makes sense. Very large entries in the D matrix mean that it takes a large amount of moment to create a small amount of curvature. So the larger the D matrix is, the less curvature you'll get for the same applied moment. Okay? So that's understanding the physical interpretations of these particular guys, right? All right, know your definitions of the special laminates. Fortunately, I have that for you in your equation sheet, so that kind of bails you out a little bit. I'll bring that in here just so we can kind of take a look at that. But yeah, your equation sheet has a lot of this information already on it, so we'll bring that in here and I'll show you that, yes, fortunately, your equation sheet has descriptions and types of special laminates. All right. So I'm kind of giving you this one for free. Also telling you the ABD effects um, here as well. So be able to identify those, and it's going to help when calculating A, B, and D on the exam if you can just say, oh, this guy is symmetric. Every B entry is zero. I don't have to do any calculation. B11 equals zero. Be on your way, right? So there you go. All right. So know your special laminates can be really useful. Know how these simplify for special laminates. Again, I was just talking about that, so take a look at the equation sheet. Be ready to sketch deformations of a laminate given a 6 by 1 vector of in-plane strains and curvatures. This is a good one, and this is kind of a question I like to pose in like the short answer question, is I'll give you, okay, I'm going to give you a 6 by 1 strain and curvature vector. Can you actually sketch for me the strains and curvatures that would exist on the laminate, right? So if I gave you like the 6 by 1, right? Epsilon x, epsilon y, gamma xy, kappa x, kappa y, kappa xy. If I gave you these values, could you then draw them? So if you had kind of a laminate that you're looking at from the side, and you had kind of like an XZ plane, and I told you, all right, yeah, there's some KY that happens here, and I give you a specific number, how is that going to deform? Well, curvature kappa Y means I'm sort of bending about the Y-axis, so you would see something that looks like that if you had some kappa XY. And remember that this would make an arc length of a circle, like the composite would deform into that shape. And so this radius of curvature R is 1 over kappa XY, or kappa Y in this case. So that's the radius of curvature for that particular laminate, and it's 1 over the curvature. So curvature has units of like 1 over meters or 1 over inches or something like that. Okay? These guys are pretty self-explanatory. Strain in X and Y, you get that. Shear strain, that's pretty self-explanatory. But some of these guys are a bit wicked. I'm not going to ask you to ever to draw kappa XY because that's a strange mode. That's like a saddling mode, right? So this one's kind of actually quite difficult to draw. Even I'm not so great at it, but it's getting your composite to look something like that, right? Looks like a saddle. That's the kappa XY. I would never ask you to sketch that on the exam. That's pretty hard to sketch. I don't even know if Mike Severe could sketch that. Come on. Actually, yes, he definitely could. That guy's a wizard when it comes to drawing. Okay, moving on. That's classical lamination theory. Now we want to move on to limited engineering properties. Let's take a look at limited engineering properties. First, for hand calculations, you should be able to calculate the mean stress on a laminate given applied loads or vice versa. All right, mean stress. Remember, let's just take a look at like sigma x. So here you've got some laminate, let's say, 4 layers, who knows? And let's say that this is, you know, z direction, and this is your x direction. And now you got some force that's applied to this, right? Let's call it Fx. Okay, you got force that's being applied in the x direction here. Well, then we know that Nx, which is the force per length, this is Fx over Ly, where Ly is sort of the dimension into the page, right? It's the dimension into the page. And we said, okay, we need to do some things in terms of mean stress, and we're talking about like elastic modulus being stress divided by strain. We know that each layer has a different stress, and so we want to be able to define what's called the mean stress. And so the mean stress in this case, sigma bar x, this is going to be equal to the average stress that exists in the entire laminate. So this is the integral from negative h on 2 to h on 2 of the stress distribution that exists on the inside dz, sorry, nx dz. Okay, so how much load, and I'm integrating that throughout the entire thickness, and I have to normalize by the total height of the laminate. All right, so this is kind of giving me an average stress. What? Headphones just went out for a second there. Yeah, this is the average stress throughout the thickness. Okay, so this is the mean stress and how you would calculate it. And this is actually going to be equivalent to nx times h. Sorry, divided by h. Okay, And so nx divided by h, this is fx over ly times h. So this is like force divided by cross-sectional area, basically. Okay? So if you're given some force on the laminate, you could just say the mean stress is the force divided by that cross-sectional area, Ly into the page, times h height, which is the thickness of the laminate, basically. Okay? So in general, we would see then that mean stress is typically written as something like sigma bar x, sigma bar y, how bar xy is equal to your vector n and s times 1 on h. Okay, so this is one way to calculate mean stress with known loads per length. All right, so that's calculating mean stress. All right, calculate the laminate engineering properties given the little a matrix. The trick here is not forgetting the 1 on h. So that's the tricky bit with that particular portion. So again, this is going to be on the equation sheet, so you'll have that to help you on your way. But let's take a look at that. I'll bring the equation sheet in here really quickly. Scroll down, scroll down, scroll down. And here we are. So this equation is what's going to be the one that's going to help you on your way with this portion of the problem. So I don't know if I can straight up copy this, but I can print screen this guy. Okay, and bring this in. So here this is strain is equal to something times loads per length times 1 on h. Well, we just said that this is your sigma bar terms. This is your mean stress. So normally we would write like the strains are equal to little a times n. Okay. So what that means here is that this plus this guy is your little a. So a lot of times you'll see this matrix here represented not in the way that you see it now, but with little h's in the denominator everywhere. And so if you write the little h's in everywhere on this guy and get rid of this, then that would technically make this here, if you get rid of this guy, then that makes this the A matrix. Okay? So if you have the little A matrix, then you can just say, all right, the A11 entry is equal to 1 on E bar X times H. So that would mean then that E bar X is just equal to A11 times H. Sorry. 1 on A11 times H. So don't forget the H. All right? That's all I'm trying to say for that little A matrix related to engineering properties. Don't forget the height of the matrix or the laminate. All right? So that's that. All right, let's move on. Calculate midplane strains on a laminate given applied loads on a laminate and engineering constants of the laminate. So I'm looking at this here. Okay. Yeah, again, this is just using kind of the equation that you see right here. Calculate midplane strains on a laminate given applied loads on a laminate and engineering constants. So that's just, again, applying this equation just in a different way. Here now you don't have the little A matrix in this sort of discussion. You have these loads, Nx, Ny, and Ns, and you have laminate engineering properties, and assumedly the height of the laminate, this 1 on H term. So you basically have everything on the right-hand side here. Okay, and so then you would be calculating this guy, right? So that all should be pretty straight ahead, all right? Get this out of here. All right, theory questions. For theory questions, understand the difference between laminate stiffness values and lamina stiffness values. This is a good one, all right? So a lamina is a single layer, right? A lamina is one single layer of unidirectional material. So lamina, you have fibers just going in one direction. And a lamina has a very well understood material coordinate system, right? One in the direction of the fibers, two across the fibers, and three in the out of plane direction, typically. Okay? So lamina, the modulus in the one direction, is the modulus in the fiber direction. This is modulus in fiber direction, right? And then E2 is across, and dot, 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 dot. All right? Shear modulus is the shear modulus in the plane. Okay, fine. That's different from a laminate, which is going to have many lamina that make it up. And laminates typically have a global XYZ coordinate system, which is aligned with kind of like the natural like coordinate system of the actual structure itself, right? So here you're going to have a coordinate system that looks like, okay, from the middle, I have X, and then going backwards is Y, and then coming up is Z. So that's the laminate coordinate system. And so now if I have some loading in this direction, this would give rise eventually to like an E bar X, which is the laminate stiffness in the X direction. Or if I were kind of loading this way, testing this in the lab maybe, then this would give rise to like E bar Y, right? Okay. So it's the difference between the laminate and lamina stiffness. And so this laminate is made of many lamina that have their own individual stiffnesses and like their own principal material coordinates. But the laminate has a stiffness in its global coordinate system, the XYZ coordinate system. Next, understand the difference between applied forces, forces per unit length, and mean stresses in a laminate. I've already kind of discussed this quite a bit, so I don't want to belabor this all that much, but more or less, like Fx, this is a force that you've been dealing with since your statics class, all right? So if you have some laminate and you just go to the tensile testing machine and you pull on it with 1,000 newtons, okay, that's a force, right? I think that's pretty easy. And so this is like, going to be in like newtons, all right? Nx, this is the force per length. And Nx, we specifically define as Fx over Ly, where Ly is the length of the laminate in the y direction, all right? This is going to have units of like newtons per meter, right? And then finally have mean stress, sigma bar x, which is Nx over h. And, oh, geez. Just trying to move this guy. Yeah. And this is mean stress. And this is going to have units of like newtons per meter squared, or what we know better as pascals. Right? Okay, so that's the difference between forces, forces per unit length, and stresses. And you can kind of calculate all of them from each other if you know the appropriate dimensions to get you from one to the next. All right, so that's that. All right, finally, understand the difference between stress in a single layer and the mean stress acting on a laminate. Again, this is important because different layers inside of the structure have different stresses, right? So I'm going to get rid of you. You're going to go away. Goodbye. So if we think back to remembering what is the distribution of stress and modulus inside of a composite, this is kind of like a really nice figure that I sort of remember drawing on the board back at one point. And you think about, all right, what's the strain? And let's say we just have some, I don't know, some strain distribution that looks like this, right? This thing is like maybe in bending or whatever. And then we have a structure that's like, I don't know, 0, 90, 90, 0. I think that's reasonable. All right, then the question is, all right, well, what's the stress that develops in each of these layers? Okay, well, we know the stiffness. If we're looking at this as like an EX. Well, stiffness is going to be stiffer for the zero layers. So you're going to have stiffness distribution that looks something like this. And the 90 layers are not as stiff in the X direction. Okay? It's because you're loading along the length of the fibers with the zeros and across the fibers with the 90s. Okay? So my modulus is going to look something like this. And we know then that the stress that develops in each layer is going to look something like the elastic modulus times the strain. And so when we think about, well, what's the stress distribution looking like here? Okay, well, yeah, we have some like linear situation going on, but as you get further and further away from the center, you're going to start running into those zero layers, right? And so you're going to end up with a stress distribution that looks more like this. Okay? And there's this jump discontinuity that exists at these layers, right? So you have this jump discontinuity in the stress because you have the discontinuity in the elastic modulus as you go from one layer to the other. So that's kind of here stressed in an individual layer, sigma bar 1, 2, K. So that is what is the stress in the principal directions in the kth layer versus the mean stress on this particular guy. And the mean stress is, remember, the average of this guy. So sigma bar x, this is 1 on h, integral negative h on 2 to h on 2 of this distribution that you just see integrated over the thickness. And in this case, because we have sort of some symmetric stress distribution, the mean stress in this case would actually end up being 0, which is kind of interesting to think about. That the mean stress in this particular case is 0 on this laminate, but the individual stresses in the individual layers, specifically like the zero layers on the top and the bottom, are highly stressed. So just because something has 0 mean stress doesn't necessarily mean that it has 0 stress in any of the layers. So you got to be careful about that. You got to watch that. All right, moving on. Onwards. Laminate failure theory. No hand calculations required for this portion of the course. RAR. That's because we know that you'd have to calculate basically every stress in every single layer, figure out the safety factor for every single layer using Sci-Hill. That would just take the whole exam time. I mean, it's ridiculous. I think you understand how important MATLAB has been in this course and why computational coding of doing this laminate failure theory is important and is required. So we spent a lot of time doing that, and I think it's going to give you some relief on the test that you don't have to do any of this laminate failure theory calculation by hand. All right. However, you do have to understand some general theory about laminate failure. So let's get into that. So for theory questions, first, understand the progression of failure for laminated composites. Yeah, we talked about this kind of very first thing when it came to laminate failure theory and said that, all right, if I have some, like let's say 0, 90, plus minus 45, symmetric, what's that load displacement curve going to look like if I just like test this, or stress strain curve? You can look at it either way. Okay? Stress strain curve, what's going to happen? Well, let's do this just uniaxially loaded. All right? So what's going to happen? Okay, load, 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 load. And then all of a sudden I'm going to hit a point where one of my layers is going to fail. And not all layers fail at the same time. And so in theory, what happens is the layers with like the weakest layers basically are going to start failing first. And we know that composites are very weak when you're loading across the fibers. So what's going to happen in this particular composite is the 90-degree layers are going to fail. And the theory says that they all fail catastrophically at the same time. Now, in practice, that doesn't really happen, but that's what theory might say. And so here, all 90s fail. Then, the zeros and the 45s continue to load with a lower modulus now because the 90s are no longer contributing to the modulus. So we have, okay, some additional load that's coming, and now bang, all the 45s fail. All plus minus 45 fail. Okay, maybe the zeros hang on. If the zeros do hang on, then you get something that looks like this until all of a sudden, bang, the zeros fail. So that's the general progression or the idea behind the laminate failure theory. In practice, it doesn't really happen like that. In practice, what happens is a much more gradual situation Like, yeah, load, 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 and then, maybe the 90s will start to fail a little bit, and then all of a sudden you'll start loading back up in the with the other guys, right? So it's much more progressive in reality, but the theory says that the layers would all fail catastrophically. The 90 layers would all fail catastrophically, then the 45 layers all catastrophically, and the zeros all catastrophically. Okay? So that's the general progression of failure for laminated composites. Now, understanding the difference between first ply failure and ultimate lamina failure theory. So, first ply failure theory would say that, all right, this would be a failure according to first ply failure, right? That theory would hold there. That's because whenever the first layer goes, you just say, my composite's done. All right. In practice, you could keep going with this thing. It could keep holding load. It could keep working, possibly. So another way that you could consider laminate failure is to go until the whole thing has collapsed and has ultimate failure. And so if you're going by this little mock example that we have here, this would be um, ultimate laminate failure, right? Um, in our class, we just stuck with first ply failure. So first ply failure is much easier to analyze and it's much less computationally intensive. Um, if you're a fire breather and you want to try to attack ultimate laminate failure, that would be a fun project, right? I actually did that when I was in graduate school, but okay, cool. We're going to work with first ply failure. It's the most conservative. It's most commonly used in industry. So that's what's going to happen there. Okay, that ends kind of like the laminate portion of the class. Then we got into like the quote unquote fun stuff. And you should be ready to like answer some questions and some questions related to kind of the special bonus topics that we had. It'll mostly be qualitative type questions, so you won't have to worry about, calculating G1C or anything crazy like that from fraction mechanics portion. It's just going to be qualitative stuff from the fun part of the class. All right. Okay, so fracture of composites. Three fracture modes. Mode 1, mode 2, mode 3. So mode 1 is the Pac-Man mode. That's mode 1. Mode 2 is the in-plane shearing mode. That's that guy sliding against each other to get the crack to propagate. And then mode 3 is the anti-plane shear. So this is like breaking the chopsticks at the restaurant, right? So that's into and out of the plane. So that's the sliding mode, right? The trouser tear methodology. Ripping a piece of paper is a good example of mode 3 fracture. Understand the energy balance associated with external loading of solid materials and how we use that to calculate critical strain energy release rate. Right. This is good to know. So we basically said that, all right, the total work that goes into a sample is the integral from some initial condition to some final displacement of the load curve as a function of displacement d delta. All right. So the total work when you're looking at load displacement for like fracture events would be the entire triangle that exists here, right? So this is total work. And we said, all right, well, when you're putting work into a structure, that work has to go somewhere. And it can go into a variety of different things. It can go into elastic strain energy, it can go plastic strain energy, it can go into the creation of free surfaces, which is fracture, it can go into heat, it can go into viscous like dissipation mechanisms, it can go into sound. There's a lot of places that it can go, right? So for our course, we just kind of assumed that we were going to have only brittle materials and we took what is kind of a lot of different mechanisms. It can go into motion, right? T is kinetic energy plus other, right? That's kind of what we started with, where we had here elastic energy, here this is plastic energy, here this is energy of fracture, here this is energy of motion, kinetic energy, and then the other sources we've talked about, viscous dissipation, heat, sound, so on and so on, right? And so how did we kind of handle this for composites? Well, we said, all right, we're going to forget about all those other nonsensical things. Well, not nonsensical, but forget about heat, forget about viscous dissipation and all that stuff. Okay, we're going to assume that it's not moving, no kinetic energy. And we're going to say that, all right, the epoxy and the glass fibers that we use mostly are very brittle, and so we don't really expect any plasticity in our particular composite samples. So what that left for us is said, okay, the total work that goes into the sample is just the elastic energy that it stores plus the energy of fracture. And the elastic energy can be easily found after a fracture event by understanding how much energy the sample gave back to you, which is how much energy was given back during the unload, right? So if you know the total work that was in, the full big triangle, and you know the amount of elastic energy that the sample returned to you, the small triangle, then the balance is your fracture energy, capital D. How do we use that to calculate critical strain energy release rate? Well, we use that in the calculation of critical strain energy release rate because we need that value, and then we normalize that by the area that was created. So the critical strain energy release rate, let's say G1C, this here is the fracture energy, D, divided by the area that was created by your fracture event. Typically, we say that the area is delta A, the length that the crack grew, and then B, which is the width of the sample. So G1C typically is going to be written as D, the energy loss to fracture, divided by B times delta A, where delta A is the crack length and B is the width of the sample. D, we typically calculate, or we typically use, sort of triangle methods to sort of figure out what that D is. And that is commonly written as 1/2 delta P times delta, right, over B delta A. Now, I said that there's no calculations required for this portion of the course, so we'll kind of just leave it there. You did some calculations for homework, so that was cool. What's important to really know, though, is the units on this are going to be things like joules per meter squared. And so I think it's important for you to know the units of fracture. Energy per crack opening area, right? So we have energy in the numerator. Meters squared is an area term. So how much energy did it take to create a crack of a certain area, right? Energy per crack opening area. So it's good to understand that when it comes to critical strain energy release rate. All right. What is critical strain energy release rate? I just talked about that. Why does our theory require the material to have a purely elastic response to use that to calculate this appropriately? Well, just talked about that, is that we made a lot of assumptions when it came to work and where that work is going. And we said it's only going to elastic energy or fracture. And that's because our samples are brittle and they don't hold plasticity. So if there's plasticity that occurs, it really makes things much more complicated. All right. Understand the difference between current crack length and crack propagation. Several people made this mistake on homework problem number 2. So I think it's part of the reason why I sort of included it here is know the difference between crack advance and total crack length, right? So what is the crack length at any particular point in time, and what is the crack length? Okay, so let's say you had a sample. I'm just going to use some square sample here. And let's say that it had some initial crack length here that we call A naught, right? And let's say, we're loading this thing up, and then the crack propagates, some additional amount, right? So here, this additional amount that it has propagated is the amount delta A, right? So the total crack length, A, is delta A plus A0. It's however much the crack advanced plus the original length of the crack, all right? So that variable A is the total crack length. You have to be careful not to use that when you're calculating like G1C, for instance, because G1C uses the crack advance, right? So G1C will use something like D, the energy of fracture, divided by B, the sample width, times delta A, right? Delta A is this amount here, right? You're not using the full crack length A, which is this amount. And so problem number 2 on that most recent homework number 11, that tripped a couple people up. So just be aware of that. What sample geometries are commonly used to evaluate mode 1 fracture toughness and mode 2 fracture toughness? So I'm looking onto this one now. This is the DCB, double cantilever beam for mode 1, and edge notch flexure, ENF, for mode 2. End notch or edge notch, I've heard it called both things. If you write DCB or ENF on the final, it's perfectly all right with me, right? What is fiber bridging? How do we identify fiber bridging in resistance curves? Good question, Dr. Hart. Thanks for asking. Right. So fiber bridging is this idea of, all right, I'm going to do a mode one double cantilever beam test, and I'm going to get a sample that kind of starts to split open and rupture that looks a bit like this, right? So if I'm loading this thing up, pulling on this guy here and here, these two hinges are going to open. My crack's going to, propagate down that general direction, right? Okay. So what's fiber bridging? Fiber bridging is, okay, I'm opening this crack and there's maybe some hairs, like some fibers that are sort of like holding on between the various layers as I'm ripping this thing open. And what's going to happen is when I first start that test, there aren't going to be those fibers that exist because I've got some pre-cracked film here that stopped fibers from being across the gap there when I was manufacturing the composite. But as I start to test and this crack starts to propagate along, right, like this all has been like fractured through, like this whole region, the top and bottom hinges where fracture has occurred newly. Then you get all these like fibers that exist inside of the crack plane that like hold on. It's almost like Velcro, right? So this is fiber bridging. Okay. And how does that rear its head in the resistance curve? Well, let's remember what the resistance curve is. So here's my R curve, called the resistance curve. On the x-axis, this is A minus, um, yeah, it's AI minus A naught. So it's the current crack length minus the original crack length. And then on the y-axis here, we have the G1C values that are calculated. Um, if no fiber bridging exists, this is going to be perfectly flat. And you'll see data points that exist on this guide that kind of hover around this central value. I think for your homework, most of them had that kind of flavor. But you could also see something that looks a bit more like this, where it rises and then plateaus at a certain value. Okay? So this would be an example of fiber bridging showing itself in the R curve. Okay. And so you might see data points that look a bit more like this. Okay. And in this case, if you do want the G1C value, you want to take the value associated with the plateau. So this is the true G1C value. When you actually manufacture a composite, there's not going to be any film, any pre-crack region built into that, hopefully. That pre-crack region and that R curve is specifically just an artifact of making those specific double cantilever beam specimens. So the true G1C value is the value that you get after that equilibrium has been reached between new fibers appearing and old fibers that are hanging on breaking, right? So that's what happens there. Okay, here we go. What is fiber bridging? Just did that. Be ready to list and describe various toughening mechanisms used to increase the toughness. Know the benefits and drawbacks. All right, we talked about a lot, so you can go ahead and take a look at that list fully. But we talked about fiber bridging, that was one. We talked about matrix methods, modifying the matrix. We talked about Z-pinning. We talked about stitching. We talked about architectural changes, right? Meaning using a 3D composite rather than a 2D composite. And we also talked about interleaving. Interleaving is including thin thermoplastic layers between composite layers, right? So I lay down my carbon fiber epoxy prepreg and then a very thin layer of like polyurethane, right? Another layer of carbon fiber epoxy prepreg, thin layer of polyurethane. Okay, that's interleaving. Okay? And that's one way to just increase or put tougher material at the interface between those composite layers. All right, making progress, almost there. Sandwich composites. Ooh, I'm getting hungry. Sandwich composites. No hand calculations again, just theory. What types of loading are sandwich structures most suited to handle? Bending. Which loading modes are bad? Shear. Okay. Sandwich structures are used to support bending. That's it. You're putting a lot of material far away from the midplane, so that increases your stiffness. All right. What is the method of transform sections and how is that applicable to a sandwich structure? I talked about this a bit, but if you have a structure that, for instance, has very stiff outer material and very not stiff internal material, so let's say here the modulus of this outer material, these face sheets, is the modulus E1, and let's say here the modulus on the inside is E2, and it is some fraction of the modulus of the upper layers. Let's say 100 times less, okay? The method of transform sections is a mechanics of materials approach that says, if I just replace the central material with the face sheet material, how thick would that material need to be in the middle to be equivalent? So I could replace the center material 2 with 1, right? If this is 1, this is 1, and this is 2. If I wanted to replace 2 with material 1, then I would need just a thin web in the center that had a width of, okay, if this is h, let's say the total length here is h, then this is h over n is all I need. Okay? I only need the width of that web to be exactly proportional to the difference in the moduli between the face sheets and the center to get an equivalent mechanics of materials response and bending. So that's really kind of an interesting phenomenon, the method of transform sections. How is that applicable to sandwich structures? Well, this is a sandwich structure. So a sandwich structure for composites is essentially an I-beam, more or less. You could think of it that way because of the way that it sort of would behave if it were all made from the same material, right? Okay, so that's how it's applicable to sandwich structures. Which laminate stiffness matrix is most affected of low strength and stiffness core? Well, that's the D matrix. And that's because you have this cubic term, right? You have the zk cubed minus zk minus 1 cubed, right? And so when you make a sandwich structure, you have very stiff material very far away from the center. Okay? And so here, like, z is very large. And so when you start cubing that z term, that's going to blow up your D matrix, right? The face sheets being on the outside are very, very stiff. And so that Q bar K multiplied by that very large zk cubed minus zk minus 1 cubed term is going to explode the D matrix. Huge changes, thousands of times difference than what you would expect from a thin laminate alone. Okay? Huge, huge differences, huge effects, right? So huge, right? Okay. What type of loading must we account for and consider when using sandwich structures? Shear. Does this type of loading have a significant influence on the classical lamination theory? Yes, it does. CLT no longer applies. So it's no longer valid. You cannot use classical lamination theory once you make a sandwich structure. The A, B, and D matrices still kind of have the same general interpretation, but because you can support shear now, you have very different deformation types, and you can no longer like assume things about how the deformation occurs. And so, yeah, classical lamination theory you can no longer use. So would be good to know that one. That's a good theory question. Put that one out there. Now the 4 common techniques for manufacturing sandwich structures and their differences. Okay, we have continuous lamination, secondary bonding. They go by a couple different names. I want to make sure I get it right, what I put in the notes. There's co-curing, co-bonding, secondary bonding. I want to make sure that I get it right based on what I said in the notes. Give me 1 second here. Okay. Continuous lamination, secondary bonding, co-curing, and liquid molding. Okay, so transfer molding, liquid molding, secondary bonding, co-curing. These two are kind of related. Um, but yeah, these are the four we talked about in class. Continuous lamination is what it sounds like. It's almost like pultrusion. Secondary bonding, co-curing. Secondary bonding will utilize under-cured face sheets to cure to the sandwich itself, right? Co-curing is, you're going to have some adhesive at the interface. Okay, fine, whatever. And then liquid molding is, all right, I just include the foam core right into my molding process, like Vardum or RTM, and then the liquid will just flow around that core, and you kind of like cure everything together. It's important with liquid molding that you have closed-celled foams or structures on the inside that are going to be the sandwich, the soft core that are not permeable, right? Because you don't want the liquid getting into those regions and making them super dense, right? Those are the four. Where a sandwich structure is most likely to fail, usually the interface between the two. That's the most likely spot, unless you have a very, very good adhesive, and even then, it's still probably most likely to fail there. All right. What test is commonly used to evaluate shear properties? That's called the short beam shear test. Short beam shear. All right. Final section, woven composites. What does it mean for a composite to be a woven composite? That means it has multi-directionality and that some sort of interweaving between layers. So multi-directionality and some sort of like interlocking. So the toes are somehow woven or connected or hooked or stitched or braided or interconnected in some sort of way. All right. Be able to sketch some 1D, 2D, 3D fabric architectures? Yeah, okay. You'll have to take a look at pictures there, but 1D, I think that's pretty straight ahead. 2D, a plane weave might look something like this. You got some over, some under. That's a plane weave for you. 3D weave, much more difficult, but you can probably do it if you had to. There you go. There's a rough 3D weave, right? That's a 3D orthogonal weave, right? You got warp, weft, and Z-toes here, all right? How are bidirectional woven fabrics made? This is on a loom. You can go to the notes and take a look at some of the YouTube videos that I posted. There's a lot of pictures in the notes too. I don't really want to draw this. Maybe I can do like a quick sketch of this, I guess. But basically you have fibers that are being held together in some sort of shed, and they're sort of clasped here in the middle, and there's something holding this guy, there's something holding this guy, and these are moving up and down, back and forth, back and forth, back and forth. And then in here, there's something that's going to pass a weft layer. So you have these, warp layers sort of moving up and down like this sort of motion. And then as they're moving up and down, a shuttle passes through sort of the through toe, the cross toe, what we call the weft toe. All right. What's the difference between a warp and a weft fabric toe? Well, we just talked about that. The warp toes are in the direction of like the loom that is shedding these guys, and then the weft is being inserted from the side, right? So that's warp and weft. All right. Do bidirectional composites typically have same properties in the warp and weft directions? Actually, no. Most often they do not. Some of them do, but sometimes they don't. Most of the time they don't. And that's because the number of like warp toes per inch might be different than the number of weft toes that you can get in per inch as you're sort of doing your shedding and you're doing your packing down as you're moving through. So, do they typically have same properties in the warp and weft direction? The answer is no. Um, and that has to do with number toes in warp or weft per inch or per length, not necessarily inch. Could be meters, could be whatever, but you get the idea. All right. Comparing 2D to 3D woven fabrics meant for composite manufacture, which are more expensive to manufacture? That's certainly 3D. Have better drapeability? That's certainly 2D. So again, how much radius of curvature can you get if you have some sort of composites architecture that looks crazy like that, some 3D architecture? It's really difficult. Can be used in a wider range of manufacturing processes. That's 2D. 2D can be used in RTM, Vardum, pressing, like all sorts of different things. 3D, you can only really do like Vardam and RTM to infuse or get the resin into this sort of interlocked region with all the interstitials. All right. Finally, then they're comparing composites made from 2D and 3D woven fabrics, which have higher impact damage, 3D. That's their whole purpose. The whole purpose of 3D woven composites is to be very good in impact damage. All right. Have higher critical strain energy release rates, 3D. Again, it's their whole purpose. Better in-plane properties, 2D. Better out-of-plane properties, 3D. That's because there is a toe of fibers in the third direction. Have higher maximum volume fractions, 2D. And that's because 3D composites have all of these like interstitial regions that are going to get filled with epoxy that won't have fibers in them. So you're just going to have lower volume fractions for those 3D woven composites. All right. Are better at resisting out of plane shear loads. Well, 2D composites can't really at all resist them, so this is 3D. That's it. That's your qualitative review. So let's move on now then to the practice exam that I sort of laid out. So we'll close this guy and we'll move over to that um, practice final. So let's pop this in here and let's just take a look at that really quick. I'm going to scroll this down. We'll just use ourselves some new space and I'm going to copy this just directly. All right. You'll find this on the Canvas page as well. So here's your sort of practice final. Oh, baby. Move way down here. Maybe I should just start a new book. Yeah, I'm just going to start a new book. All right, that'll just be easier. Killing me. Killing me, computer. You're giving me an early grade. All right. For crying out loud. Yeah, there we go. Okay, here we are. You work from Walking Tool. Want to know if you can replace part they typically made out of aluminum with carbon fiber epoxy. Your exam's going to look like this. I'm not going to sugarcoat it. This is what it is. You're going to get material properties for epoxy and some fiber. And I'm going to ask you to step through the entire process. Calculate lamina properties, calculate stiffness matrices, compliance matrices, do some calculations related to failure strength, do some calculations related to lamina and laminate properties. Okay? So you got to be able to do this. That's this whole class, starting from constituents going all the way up to a laminate. So let's talk about this. Number one, calculate lamina properties of unidirectional lamina made using constituents if the volume fraction is number. Okay, this is helping psi, which generally is property of the composite is equal to property of the matrix multiplied by 1 plus xi eta vf all over 1 minus eta vf, right? For E1, you typically use xi is infinity, which is rule of mixtures. Same thing with nu 1, 2. E2, you'll use xi is equal to 2. And G1, 2, you'll use xi is equal to 1. So those are how you do your calculations for lamina properties. Next, populate in-plane principal compliance matrix of this lamina. All right, so compliance matrix in plane, this is a 3 by 3. Not going to ask you to do anything related to 6 by 6. So this is a plane stress compliance matrix, a 3 by 3. And once you have lamina properties, this is pretty straight ahead. The 1, 1 entry is 1 on E1, nu 1, 2 on E1. Here we have 0, nu 1, 2 on E1, 1 on E2, 0, 0, 0, 1 on G1, 2. So that is your compliance matrix. No problem. populate in-plane principal stiffness matrix. So the stiffness matrix, Q, is just this inverted. So if your calculator has the ability to do that, okay. You got to show me what you're doing if that's how you're getting it. Okay. You got to tell me this is the S matrix and I inverted this on my calculator to get Q and here's Q. You got to make that like very clear for me. Otherwise, if you don't have a calculator that has that function, you can still calculate the stiffness matrix using sort of equations from the equation sheet. So the stiffness matrix Q11 can be calculated as E1 over delta. Q12, this is negative E1 nu 12 over delta. Q22, this is E2 over delta. Q66 is 1 over, sorry, is just G12. And all other Q's are 0. And so what is delta? Well, delta is a variable that it's actually the determinant of the compliance matrix. And so it can be gotten from material properties as well. And this is on your equation sheet too. If we scroll all the way up here, it's this delta here is the determinant of the compliance matrix. And I'll just write that here. It's 1 minus nu 12 times the ratio of moduli E2 to E1 squared. I want to make sure I get that correct here. Oh, sorry, it's nu 12 squared, ratio E2 on E1. So there we go. That's delta. So if you don't have the ability to do this on your calculator, that's fine. Just utilize this. It's just a little more long form calculation, but you can do it. You're engineers. Don't enough calculation in your life. All right. Next, number 4. If a single lamina is loaded off axis at an angle of theta is 45 degrees with some stress, calculate the factor of safety using psi Hill. All right. So psi Hill, we recall, is going to be something like sigma 1 over F1 squared plus sigma 2 over F2 squared plus sigma 6 over F6 squared minus sigma 1 sigma 2 over F1 squared. This is equal to 1 on the safety factor squared. Don't forget the square. Don't forget the square. Ah! All right, I know someone's going to do it. All right, don't forget that safety factor squared. So what we need to execute that portion of the problem is we need stresses in principal material directions. The problem gives us stresses in global coordinates. This is what was given in problem. So we need to actually transform from global coordinates down to material property coordinates. And so remember that we do that using the transformation matrix T. So you'll have to transform stresses in the global coordinate system to stresses in the material coordinate system using the transformation matrix T, which is going to use cosines and sines of the angle that's given here. In our particular problem, it's 45-degree angle, right? Okay, so after you make the transformation, plug that into psi Hill. And remember when it comes to psi Hill, what failure strengths you're using. So remember, failure strength is different in tension and compression. And so if sigma 1 is greater than 0, use F1T. Sigma 1 is less than 0, use F1C. Same thing for the 2 direction, blah, blah, blah. You've done this. You understand. Don't forget the safety factor squared. Oh my God. I know someone's going to do it. I know it. Is it going to be you? We'll see. Lastly, calculate A11, B11, D11 entries if you have a certain stacking sequence and a total thickness of 0.6 millimeters. All right, I've already shown the ABD matrices. Some things to watch out when you come to this portion of the exam is, can you identify it as a special laminate and immediately make some conclusions? In this case, you could identify this guy as a special laminate. This is 0, 92 symmetric, so 0, 90, 90, 90, 90, 0. So this is symmetric. That means that the B matrix is 0. If you just write on your exam, symmetric Bij equals 0, that's all you need. Don't do the full calculation. Save yourself some time. The full solution for this is available on Canvas if you want to take a look. Other than that, I think that'll conclude the review. Uh, Good luck. I'll be around tomorrow by email. I actually won't be in the office tomorrow, but I'll be around by email, and I'll be around on Teams if you want to chat with me on Teams. So good luck to you. I'll see you on Tuesday. Rawr.